In this video, we continue with our study of vectors by particularly looking at their components and how we could use those components to compute magnitudes. This is going to be used as an alternative to the graphical techniques. We want some kind of formula-based or symbol-based ways to manipulate these vectors as well. One way to define vectors is using building blocks. So if we imagine our three-dimensional axes in x, y, and z, with those axes, we can imagine taking one step, so unit length or length 1, and calling the direction in the positive x direction, calling that a vector. It has magnitude, it has a direction. We call that I. We also then come up with a name for the positive y direction. Unsurprisingly, that gets the label j, and if we also go vertically with length 1, we give that the label k. By creating those three vectors, we've actually created the possibility of generating any vector we like, because if we imagine going out to some point in x, some point in y, some point in z, and connecting it back to the origin, then we can achieve or get from that start point to the end point by taking our I vector and then multiplying it by some amount, basically taking that many copies of the I vector. So I vector, I vector, I vector would be 3 steps in the x direction. And then we can do the same thing in the y direction by adding up j vectors, and then the same thing vertically by adding up some combination or some multiple of the k vectors. And so this is a really nice way to be able to break down coordinates or relate coordinates to vector notation. Once you do that a few times, though, we recognize very quickly that the I, j, and the k always represent the same things. We always put them in the same order. So the thing that distinguishes one vector from another is the coefficient out front, this v1, v2, v3. And so most of the time in this course, we're going to associate the components themselves, just those coefficients, put them in angle brackets to indicate that we're talking about a vector specifically, and we'll just put the numbers that correspond to how much in the x direction, or how many I vectors, how much in the y direction, or how many j vectors, and how much in the vertical direction, how many k vectors. And that is called the component representation of a vector. Any vector that we can draw can be rewritten in this numerical format. As you read other textbooks, you may see other notations for vectors, sometimes square brackets, sometimes round brackets, may or may not have the hat, sometimes they use capital letters. There's definitely some variation, but at the end of the day, whenever you see a list of numbers like this and it's representing a vector quantity, you'll recognize that in how it's being used from the context. For this course, we will use either the IJK notation with an addition in between, or we will use the angle brackets going forward. As a quick little demonstration, here we have the graphical form of vectors, and we can convert those into components fairly easily. v1, for instance, here is 2 steps to the right. So if I think of just talking about the I vector in this direction, that would be in the positive x direction. Compared with the y direction, that would be a j vector if we treat y as vertical in this two-dimensional diagram. So v1 could be 2 i's, or we could say v1 equals 2 in the x direction and 0 in the y direction. There's no vertical component to that vector. Taking a look at v2, here we have 1 I and a j, or we can write it in the component format of 1x and 1y, 1 step to the right, 1 step up. We get something a little different if we look at v3, which is that we do have a step to the right, but then we have 3 steps down. Well, I've already captured this a bit intuitively. We can subtract 3. Instead of going up 3, we can go down 3. We achieve that with a minus sign. We can subtract 3 j's. Or we can write that in component form as the coefficient of the I, that's the 1, and the coefficient of the j, -3. And last but not least, we can look at v4, which is backwards 2, so minus 2 i's in the x direction, and then up 2, so plus 2 j's. Again, or in component form, negative 2, positive 2. Just taking or capturing those coefficients and putting them in the order of I and j. With all of that in mind, take a moment to think about these vector component representations, and then think about how we could use those to help us compute vector sums. Take a look at v1, take a look at v3, and then imagine what you would get as the sum of those, either by drawing the picture or by looking at the components. Pause the video for a moment, and then we'll check in. All right, let's do this quickly in both ways. If we take v1 plus v3, v3 is like this. We already have v1 drawn out. So v3 added on the end would look like this diagram here. And so the sum would be this combined vector in green. That would be v1 plus v3. Well, we can see that that would be 3 to the right and 3 down. So we'd expect that to be 3, negative 3, which is in fact our list here, as b. However, if we think of how we built this diagram, we could do exactly the same thing going straight from the components. v1 was 2, 0. v3 was 1, negative 3. What do we do when we add vectors on the plane? Well, we take the x components that we had in the original vector, the first vector, and then we add in the component of x from the second vector. So we take this 2 and this 1, and that gives us a 3 for the x component. We then do the same thing for the y component. So we have 0 minus 3. We have then at the end a new vector. The sum vector is 3 to the right and 3 down, or the 3, negative 3 vector in component notation. If we do that again, take a moment to practice and ask yourself what v4 minus v3 might be. Pause the video for a moment, and then we'll check in. All right, we have v4, which was negative 2, 2, and we had v3, which was 1, negative 3. Now we just have to be a bit clear about how we handle this negative sign. v4 minus v3, we can replace each of those with the components we started with, now with a minus sign in between. And we do exactly what you would expect. We would take this negative 2 and we would subtract the matching x component in the next vector. So we'd combine those two with a minus sign because of the subtraction between the vectors. So we end up with negative 2 minus another 1. That would be negative 3. And we repeat the same calculation with the y components. 2 minus 3 is going to be plus 3. That would be 5. Does that make any sense? Absolutely. If we draw that same situation out, we're going to draw it down here to give ourselves enough room. Here we have v4. And then v3 would ordinarily be down like this, but we're going negative v3, so we go in the opposite direction. And if we do that, we are going to obtain a vector that is 2 steps and then 1 more step, minus 3 steps to the left. And then in the vertical direction, we would be going up 2, and then we would be going up 3 more. So we'd have that total vertical component of 5. Once we have the component form of a vector, we can also easily calculate the magnitude. And this is based strictly on Pythagoras. Imagine if we had components that was this much in the x direction, this much in the y direction. Let's call it v1 and v2 as scalar values. Then the length here of the hypotenuse, because this would be a right angle, is v1 squared plus v2 squared, all square rooted. Notice if we have a 3-dimensional vector, the length is exactly the same, but then we just add in the third component squared. So take a moment to consider what the length of the vector in component form 2, negative 3 might be among the options here. We'll check in a second. All right, well, if our vector is 2, minus 3, then that in this idea here is what we called v1 and v2, the scalar values. And so the length is simply the square root of 2 squared plus negative 3 all squared. Notice, like with Pythagoras, we expect all the quantities to be positive by the time we're done because the square makes everything positive. So we'd have the square root of 4 plus 9 or the square root of 13, answer C. With that, we have covered all the fundamentals of vectors as direction and magnitude quantities and how we can represent them in components and then use those components to compute interesting properties like their magnitudes.